Thank you. Okay, so what I want to tell you today is I want to carry on with the Hitchin vibration, which gives us the integrable system. So we were looking at Higgs bundles and integrable systems. And the main system that we're going to have related to Higgs bundles is what Hitchin introduced back in '87, which was the Hitchin vibration. So today, we're going to look at the Hitchin vibration. And this vibration, he defined it for complex, he did it for classical complex Lie groups, but you can extend it to other Lie groups. We're not going to go into any further extension of these. So we're going to use his approach from back in '87 Hitchin, which relates the Hitchin vibration for GC Higgs bundles. So let's remind ourselves we're working on a Riemann surface which is compact. So our X from the notation from this morning is going to be a compact Riemann surface of genus at least 2 as yesterday, and we're going to call again K the cotangent bundle of the Riemann surface. And recall that we saw what complex Higgs bundles, so recall that a GC Higgs bundle is a pair, we're going to say P phi, or P a principal GC bundle, and phi a holomorphic section of the adjoint bundle associated to P tensored with K. But we went further and we said that if GC is a subgroup of the general linear group, then we can just think of them as classical Higgs bundles with some extra information, and that's what we're going to do today. So today we're going to restrict our attention to the cases of GC being subgroups of general linear group. So restrict the attention today, and also the next 2 lectures, we're also going to do the same, restrict attention to GC of type A, B, C, or D. So these are subgroups of G, L, and C. And so what we saw yesterday is that then the Higgs pairs, the Higgs bundles, are really classical pairs, so E phi with extra structure. Using these pairs, the Higgs bundles for complex groups, and we're going to view them as classical vector bundles and sections with some extra structure, which we'll see what it is. We construct the moduli space of Higgs bundles. What we said yesterday was MGC. And now we want to understand how to obtain an integrable system from this moduli space, how to do it for each of these groups, and moreover, understand certain dualities that appear for this moduli space. So through mirror symmetry, what should happen is that the moduli space of Higgs bundles for a complex group should be dual to the moduli space of Higgs bundles for the Langlands dual group. So if we have a complex group, let me just put here, we don't need this, so we're going to keep the groups that I want you to keep in mind and the dualities that I want you to keep in mind for when we look at the integrable system are the following. If we have a group GC here, we're going to have a Langlands dual group. These are, if you haven't seen them before, you get these groups by looking at dual roots. So it's not a difficult exercise to try to construct what these Langlands dual groups, but I'll just tell you what they are so you can remember. So for GL and C, we're self-dual. We're going to put GL and C. For SL and C, you're going to have PGL and C. For the special orthogonal with even degree, SO2N C is going to be self-dual again, SO2N C. And for SP2N plus 1 C, it's going to be dual to SP2N C. So here we have all the options that we're going to be looking. And one thing that we're going to see today is that once we construct the integrable system for the moduli space of Higgs bundles for one of groups in this column, SO, yes, thank you, SO, thank you. So once we construct the moduli space for one of these groups and we look at the Hitchin vibration, there was a conjecture from Yao, Strominger, and Zaslow that said actually mirror symmetry should be seen in terms of the fibers of the vibration. So the fibers of the vibration for one of these groups should be dual to the fibers of the vibration for the dual group. And that indeed you can see it, and you can see it through spectral data, so it's through the fibers of the Hitchin vibration in a very nice and neat way. It was first seen back in 2002 by Thaddeus and Housel in the case of SL, but then it was extended by many people to many other groups. So it's a very nice, one of the very nice applications that this integrable system has, how the Langlands duality in this case. So what is this vibration? We're going to try to understand a natural vibration that Hitchin defined. We're going to call the base space AGC. So this is going to be our Hitchin base. And this is going to be our Hitchin map. And now I'll tell you how to obtain it. So for any of the groups that we mentioned before, we can construct the ring of we can take the ring of invariant polynomials, and we can select a basis, a homogeneous basis. So taking or let P1 ... Pk be a homogeneous basis of invariant polynomials for the Lie algebra of the Lie group we're looking at, so it's the complex. Once we take these invariant polynomials, they have some degree. Anytime you take any basis, they will have these same degrees. So let B1 to Bk be their degrees. Then what is the Hitchin map? The Hitchin map, what it does is it takes a representative of a class here. So you have E phi. And we're going to apply the invariant polynomial to the Higgs field and come back here to the base. And that's going to be our Hitchin map. So then the Hitchin map is H sending a pair E phi to P1 of phi dot P2 of. What is this telling us? So who are these PIs of, sorry, PK here? PK of phi. These PKs of phi, so where P, so PI of phi is inside the zeroth cohomology, so it's a section of K to the DI. It's a differential of degree DI. Now this might seem a little bit abstract. It comes back to the definition we were looking here, and that's why I put it. Because we're looking at a principal bundle and the adjoint bundle associated to that principal bundle. Our Higgs field, we're going to look at matrix groups, so our Higgs field will be a matrix acting on this vector space over each point, and we're going to have these polynomials applied to this to the Higgs field, and that's going to be our basis. So our basis will be the sum of all these vector space, all these spaces. So let me put it here. It's the sum from I equals to 1 up to k of H0 sigma k to the di. Now let's get hands-on on what are these spaces actually and what are they telling us. So just as an example to start with, the first example Let's look at the general linear group. So let's look at GC equals to G, L, and C. Then a basis of invariant polynomials can be taken to be just the traces. So the polynomials are just traces. So a basis is trace of the matrix to the I, for I equals to 1 up to n. So once we have the basis, we can apply that to our Higgs field. So then the Hitchin map, H, will send a pair E phi just to applying this thing to the Higgs field. So this will be trace of phi to the n. Now, what's telling us this? I'm just, up to now, just told you what the Hitchin map does. You take a Higgs pair and you send it to that basis. What are the properties of this vibration and why is it so important? There are several properties, but one is that it makes the system be an integrable system. So the Hitchin map, it makes or gives an integrable system. So what do we have in particular? The dimension of the base, A, G, C, being half the dimension of the space. It depends on the group. Yes, the highest exponent. Yes, sorry. So the k are the degrees of the polynomials. The k will be the highest exponent. Depending on the group, it will be the rank. In our cases, it will be the rank of the group or half the rank of the group. Is that enough information of decay? No. Yes, so to know that the dimension is half, you have to, we're not going to show it, but you have to see what the decay is. So the di's are the degrees. Just by definition of what degrees of invariant polynomials are, this is the highest exponent. The highest exponent. And the dimensions of these moduli spaces will depend on the dimension of the group. So you have, is it 2 dim G C 2G minus 2. Not for GL, but for the other ones. But I think so. What, sorry? There's an extra 2, this one, right? Yes. Yeah. Okay, so I want to understand one of the important facts is not just that it's an integrable system, but the fibers are, in the smooth fibers, are compact abelian varieties. So the smooth fibers, and this is for any of the groups, so the smooth fibers of the Hitchin fibration are compact. So it's a proper map, compact abelian varieties. The Hitchin map is this map that sends this, and it's a proper map. It is a proper map. And in particular, the smooth ones are abelian varieties. So what we're going to see is how to construct these abelian varieties. What is the information that the basis is giving us? What's the information that the fibers are giving us? You'll see the relation between the dimensions, and you'll see what the invariant polynomials are for each group. Once you have the abelian varieties as your fibers, the duality between these groups and these fibrations will be more clear because you'll have duality as two abelian varieties. So once you have an abelian variety on one side, you can check what the dual is, and it will be, in fact, the data for the other group. So what is what we call the spectral data? Once we have the Hitchin map, the way of describing this integrable system, so we can describe the integrable system via spectral data. And what is spectral data? It is the information that we're getting from a point in the base. The point in the base will give us a curve, a spectral curve, and the fiber. The fiber will be described by a certain line bundle or vector bundle, in some cases, over that curve. So the spectral data is given by a spectral curve, so given by a spectral curve. We're going to call it S, and I'll tell you what it is, and a line bundle on S satisfying some conditions. Conditions reflecting the nature of the group. Reflecting the nature of GC. So what is the spectral curve? The spectral curve S is going to be cover of your Riemann surface given by a point in the base. So defined by a point in the Hitchin base. And how do we define it? Well, what we're going to do is define it through these invariant polynomials. So the way that you can do it is by saying either taking the invariant polynomials or directly going to the characteristic polynomial of the Higgs field. So S is the zero set, is defined as the zero set of the characteristic polynomial of the Higgs field, so the determinant of phi minus lambda times the identity. And this is going to be inside the total space of the canonical bundle, so total space of K. When I tell you appropriately what lambda is, so I haven't told you what this variable, how to think about this variable, but what you're going to do is when you take the total space, or when you take K as a line bundle over your Riemann surface, and you call this phi, where once you take your projection of your canonical bundle over your Riemann surface, you consider lambda the tautological section of the pullback of your canonical bundle to its total space. The tautological section of the pullback inside the total space. Okay. So you're having a line bundle, and you have your projection of your line bundle to your Riemann surface. You pull back that line bundle to the total space, and you have a tautological section, the evaluation map. That's the map that you're going to put there. So how does this relate? How does this relate here? I told you it was given by a point in the Hitchin base. How does this relate back to what we said the Hitchin base was? The Hitchin base was the invariant polynomials applied to your Higgs field. So the relation is the following. In fact, for most of these groups, if you want to consider basis of your invariant polynomials, homogeneous basis, they are given by, sorry, is there a question? They are given by coefficients of invariant polynomial, coefficients of characteristic polynomial. So note that a basis of invariant polynomials is given by the coefficients of the characteristic polynomial of the Higgs field. So what do I mean with this? It might be a bit confusing in the beginning to think about this approach, but it's really from linear algebra. You're trying to see what are the coefficients of your characteristic polynomial. And in order to understand what are these coefficients, you can actually take a basis of homogeneous polynomials. However, you have to have a caveat here, except for SO 2 and c, and we'll see what happens in this case. In this case, the last coefficient of your characteristic polynomial is actually the square of an invariant polynomial. It's the Pfaffian square. So let's take a look at what this vibration is in many cases so that we get hands-on on how to calculate. Yes, so we're using a particular representation. We're using the representation from the paper back in '87. That's the canonical representation. Yeah. Yes, it's the exponent. Yes, sorry. Here is exponent plus 1. Yes. Yes. And you can go the other way, right? You can look at your ring of invariant polynomials, choose a basis, and the degrees of that basis will be those ones. So you can do either way. So in general, using these polynomials, you'll have, these polynomials will be the coefficients of this determinant. Right, okay, fair enough, yes. So the spectral curve, well, you will still need a polynomial. What, sorry? For these classical groups, we can still do it, and you'll still have power. So maybe if you take another representation, you are going to be taking different combinations of these polynomials. Okay? But so the spectral curve, if you wanted to do it generically, what you're asking, you take invariant polynomials for any representation, then you go into the realm of cameral covers, where you can define anything for any, the cover you define for any group. Right, But and that you can see it from the fact that your invariant polynomials in the basis, you won't have that trace. So when we look at the invariant polynomials or the coefficients of characteristic polynomials of matrices in each of these groups, we're going to see, for instance, if your group was off diagonal, square off diagonal, then any degree polynomial won't be there. So I take the traces and then they all vanish. That means that any odd degree, means polynomial has only even degrees. Then it means my curve actually has only even degrees. So let's take a look at some examples and see what are the generic properties of this curve. Because once we do it for all these cases, it will be very clear how to actually work with them. There is, of course, the need in many cases to go to more generic definitions where you take any group. And from the physics perspective, Motohiko's question is very important because from the physics perspective, you might want to look at the Hitchin vibration for minuscule representations, or you might want to look at the Hitchin vibration for other types of representations. And then you have to do it that way. But you can still do it looking at, and I'll tell you in the last lecture, when I tell you about other correspondences, one of the things that you can do is you can look at different representations of your group, and you can relate it to the original one. So you still use your polynomials, you just take powers or exterior powers, etc. Yes. I think it's that joint, but we'll see. So the way of understanding PGL that I always had, and I'll show you how it is by looking at SL and thinking of the dual. So I don't know if that helps. It is cheating, yes, it is cheating. What's the usual representation that people take? People that work with P. Yeah. PGL. So let's take a look at some examples of what are these objects. We're going to keep the definition and keep the groups here so that we remind ourselves what they are. And let's say here what the spectral curve was in the generic case. So we said it was the zeros of the characteristic polynomial, so that of phi minus lambda times the identity. This was inside the total space of K, and given that we consider K, so since we call pi the projection from K to sigma, we can, and this is in the total space, we'll use also pi, so let also be pi the projection or the cover that S gives, so S on sigma is the cover, so this is a cover of the surface. And the degree of the cover will be given by this highest exponent plus 1. So of degree dk plus 1, and we'll see what it is in each of the cases. So consider the first group, G, L, and C. Here our Higgs field, so the Higgs pair, the Higgs bundle, E phi, has, all we know is that E is a holomorphic vector bundle of rank n. So has E a holomorphic vector bundle of rank n, and phi is a holomorphic section. So take the basis of invariant polynomials, we said it was given by the traces. So the determinant of phi minus identity can be written as x to the n. So this is the determinant of a section with values in the canonical bundle of a vector bundle of rank n. So it's over each point is a vector space. We have an n by n matrix acting there, GLN matrix. So we're going to put it here, and we say these characteristic polynomials x to the n, a1 x to the n minus 1 plus a n minus 1 x plus, lambda. Lambda a sub n, where who is a sub I? A sub I is a trace of phi to the I, and this is a section of k to the I. So all we've done is taken a basis of, all we've done is taking the characteristic polynomial of our Higgs field as a matrix. We're working with matrix groups. We write this characteristic polynomial. Our variable now is the tautological section, which means the zeros of this polynomial, when we take the zero set, that will be an n-sheeted cover of the Riemann surface. So the zero set gives an n-sheeted cover of the Riemann surface. And the cover is the spectral cover, so S, and this is the spectral curve. So the form that your Higgs field takes, we said if we have a subgroup of the general linear group, so any of the other ones, we take a classical Higgs bundle and we put extra conditions. The extra conditions being sometimes, for instance, that the Higgs field is traceless, so we won't have the trace inside. In other conditions, it will be it's off diagonal. Then we won't have odd degree polynomials. We'll see all these cases, but the point being, the structure of the group is reflected on the Higgs field, and that's reflected on the curve. So whatever the Higgs field is telling you will appear on your curve. Whatever the vector bundle tells you will appear on the line bundle we'll take on this. Yes? Yes. Yes, because you don't have all of them. So yes. So there is a formal, this is just so we can construct the spectral data in, a stunt. Yes, that will work. And that will work. That's the appropriate way. And this comes back from 87, but also from Bobbil, Narasimhan, and Ramanan's paper on theta characteristics. So there is a very nice description, and we'll be using a lot of their results. So look, as a side note here, we said look not only at Hitchin 87, and yesterday I also mentioned Hitchin 07, but also Bobbil, Narasimhan, and Ramanan's paper, I think it's from 89. Yes, indeed. For exceptional Lie groups. And that's the way that you have to do it if you want to define everything. Probably they don't use thinking diagrams in any of these papers, but I'm sure that it comes from there, probably. But I would suggest if you want to actually look at the spectral data for these groups, you'll see you don't need to go to all that. Just following, and in fact, for going hands-on to spectral data, you can go to the paper from 07 and they had G2. G2 and maybe E7, but G2 for sure. It's interesting. It's self-dual, but the duality of the Langlands duality is not a duality over the same point in the base. It goes to a different point. But anyway, so here it's just in an hour. I want to tell you the Hitchin vibration for all these complex groups. So it's going to be roughly speaking. And if you want more details, you should go either to the papers or to me, and I'll tell you where to find the details. Okay? But we want to go through these through the spectral data and understand the duality, so then we can look at other integrable systems inside. So here we define the spectral curve by looking at the determinant of your polynomial. We're taking matrix groups, so your polynomial will be very easy to evaluate. You take your polynomial, and that gives you the polynomial for or the equation for a curve. So the zero set gives you the spectral curve. Now, what is it going to be the spectral data? We said for the spectral data, we also have a line bundle. And the way of obtaining that line bundle is by looking at the co-kernel of the Higgs field. So here we looked at the determinant. We look at the kernel and co-kernel of this map. So let me show you. So the spectral data. The spectral data in this case is given by the Jacobian of this curve. So what do we mean by this? I.e., the smooth fibers of the classical Hitchin fibration. Classical Hitchin fibration are Jacobian varieties. So in your fibration, you'll have the basis of the point. So you have your fibration here, MGC. You map it over A, GC here, where GC is the general linear group. So GL and C, GL and C. And your smooth fibers, a point in the base, will define a point here, A inside the base, defines S, and over that S, we have the Jacobian variety. So now we can see the abelian varieties appearing. I need to tell you how to obtain that abelian variety, right? If I give you a Higgs bundle, how do you recover a point in that abelian variety? And vice versa. If I give you a point here, how do you recover your Higgs field? So how do you do this? Well, in fact, it's this tautological section that will play a very strong role. So let's start from the abelian data and recover the Higgs field. So note that given a point in the base, so given an n-to-1 cover, given a smooth n-to-1 cover of the Riemann surface, S of sigma, we can take line bundles on it. So, and a line bundle L on S. We want it to be in the Jacobian so that we make the correspondence, so of 0 degree, of degree 0. How can we obtain the Higgs field? So we can construct a natural classical Higgs bundle by taking the following. I need to tell you how to obtain your vector bundle and your section. So what you're going to take is you're going to take the direct image of your line bundle. So your vector bundle E will be the direct image of your line bundle. This is an N, this is a rank N vector bundle. And the way that you're going to construct your Higgs field is by pushing down the tautological section. So since to construct the Higgs field, phi will be the push down of your tautological section lambda in the following way. Lambda was a section of the pullback of K. So since lambda was a section of the pullback of K, is a section of the pullback of K. At the level of the spectral curve, we have a map just by multiplying by lambda from L to L tensored with the pullback of K. And this is just by using lambda. This is at the level of the spectral curve, so at the level of the n-to-1 cover. But now, by definition of direct image, if you put the direct image here, and put the direct image here, you'll get a map. Wait. So then, using direct images of sheaves, you can look at H0. In principle, you should do it first locally. So you should do it first on inverse images of open sets. So you take an open set, you have pi, it goes from S into sigma. You can take an open set here and look at pi minus 1 of your open set here. And so once you can look at the local sections of your line bundle and local sections of your line bundle tensored with the pullback of K. And so you obtain by multiplication of lambda a map from these local sections. You push that down to the Riemann surface, and once you push it down, you'll have a map from L to L tensored K. So pushing down to get a map phi from L to L tensored with K. This is just in 3 lines what in the papers appears in many pages, okay? So there's details to be calculated. This is first local, then we have to do it globally, then we have to see that everything agrees, and we have to see, for instance, that stability is preserved. I'll make a comment on stability in a second, but the rough idea for you to remember, yes? Yes, thank you. From E to E tensor K. Using, yes, thank you, Motohiko. Using this definition of E. Yes? So, exactly, that's my, let me just address Johan's comment. So I want to make a comment about stability, or in fact, that's related to why I say a smooth, given a smooth n to 1, n minus 1, n to 1, sorry. I shouldn't do that. N to 1 cover. So you're asking, why does smooth of n to 1 covers relate to generic fibers or smooth fibers? So here are a few things to remember about the Hitchin vibration, which are, the first thing is, what is a smooth fiber of the Hitchin vibration is the fiber over a smooth point. So first we need to define what smooth points are in the Hitchin vibration. Let me keep these. Let's take these away and no. Yes, that's the point. But they will be smooth, those fibers. You might have other smooth fibers over singular points, but that's not what we usually refer to as smooth fibers. Yes, no. So let me just put it here. Yes, is there another question? Yes, it's a vector space. Because it's the sum of spaces of differentials. So it will mean that the point that it defines it, I'll just write it down. A smooth point in the Hitchin base will mean that the curve that it defines is smooth. That's the convention. So, which is different indeed from looking at a vibration. So what do we call smooth? Smooth point in the Hitchin base equals a point defining smooth spectral curve. So yes? So what do you mean as critical point of the vibration? Okay. Yes, because you're looking at the polynomial that you're getting. You're differentiating the polynomial. You're looking for double zeros. Yes. So the way to do it, yes, you look at your polynomial that defines your curve. You look at the points where that polynomial gives you a singular curve. So you differentiate that polynomial. You look at common zeros. Yes. Is that okay? This will satisfy it, but there might be other points. Yeah. No. Yes. However, those smooth fibers are over the singular set in the Hitchin base. Right? Aren't they? Is the point in the discriminant locus? Yeah. The fiber itself is smooth. Yes. Yes, indeed. And we go back to what we were talking yesterday. That's a great point. So what are we saying? We're saying that the spectral curve is smooth, which means the characteristic polynomial in particular. So in particular, the characteristic polynomial of phi does not factorize, so it's irreducible. Which means our Higgs field doesn't preserve any subbundle, as we saw yesterday. So the Higgs field is stable. So phi is stable. So in the Hitchin base, in our vibration, In the fibration that we have here, we'll have the regular locus, which is the one that we're studying here, looking at the fiber. But there will be, as Richard was saying, smooth fibers over other points. Those other points and those other fibers are going to be harder than these. These ones described generically by Hitchin. Okay. There will be compactified Jacobians in these cases, and in other cases you can have compactified prime varieties and products, and you can understand them. But it's much easier to look just as the generic locus. So smooth points, and these give us the generic locus. And what we're saying here is that from here, the discriminant locus in the Hitchin fibration, in the Hitchin base, is the set of points giving us singular spectral curves. The points giving singular S's. So points in the Hitchin base will give curves. You can use different methods to show that a generic curve is smooth or not. So in this case that we said, it was Jacobian of S, where S was the zero set of a polynomial that was lambda to the n plus a1 lambda to the n minus 1 plus an. When you look at this, you look at it as a linear system, and that I would suggest going back to BNR to see how it works very well. But you look at it as a linear system, and you check what are the base points of your system. So using Bertini to see what the points are, Bertini, to understand the base points of the linear system. Linear system. You see that generically this is smooth. You see that the generic curve is smooth. And this is why we talk about generic points in the Hitchin base as the one giving us generic curves. The generic spectral curve will be a smooth curve. It will have Higgs bundles which are automatically stable. So generically we can do all this work. And what we're saying is if you have a classical Higgs bundle, you take the characteristic polynomial, you get the curve. On the curve you look at line bundles, and the push down of these line bundles will push down to give you the vector bundles downstairs. Now, you're talking about the moduli space, so here you fixed, to obtain the moduli space, you fixed the rank, and you've also fixed the degree. And that's why we're talking about the Jacobian. Because even though we're pushing down things of degree 0, which means when we push them down, these vector bundle will have some degree. It's a fixed degree, and by twisting by some fixed line bundle, we can put it back to being the degree that we want. So there is a correspondence between just talking about the Jacobian and talking about the moduli space with fixed degree there. Since we said that for Higgs bundles for other groups, we take the Higgs pair for the general linear group and we put extra conditions, you can imagine that for looking at the Hitchin fibration, if we take Higgs bundles for other groups, we have to put further conditions on this curve and on the line bundle. And if we put the appropriate conditions, when we push down with this method, we should recover Higgs bundles for other groups. So what are the type of conditions that we would need to put? So the type of conditions will depend on the group. What happens, for instance, if we look here at the special linear group? So if we look at the special linear group, if you look at GC being the special linear group, cell NC, what are the conditions that we mentioned yesterday and that Richard mentioned for us that give us SL and C Higgs bundles? So a Higgs bundle E phi has a rank n vector bundle E, which has trivial determinant. So the top exterior power is trivial, and the Higgs field is traceless. So what are the conditions that we would need to put on the spectral data to recover the vibration for S, L, and C Higgs bundles? We look at the conditions here, and we see that the conditions on the Higgs field tells us that the trace of the Higgs field is 0. So what will happen is that instead of having here a coefficient, we'll just lose it. We lose this one, right? Yes. Lose it. What, sorry? This one? I was doing the other way, sorry. Yes, thank you. Yes. So we're losing one coefficient here. The trace, this was trace of phi lambda to the n minus 1 here. We lose it to reflect the nature of the Higgs field, and now we need the nature of the vector bundle to appear. So on this curve, we need to put a line bundle. We need to do the same that we were doing here. We have an n-to-1 cover, and we need to take a line bundle such that this direct image has trivial determinant. So we need to be able to use some condition on the determinant to obtain the appropriate Higgs bundle. If you push down the tautological section, it won't be hard to see that what you get is a traceless Higgs field. But the tricky thing in this case is to understand how to get the trivial determinant. So for that, you go back to VNR, so VNR Riemann remanence formula, to understand what is the determinant bundle of the direct image of a line bundle. Because this is the object that we want to be trivial. This is what we want to be trivial. But what they tell us is that this object actually can be expressed in terms of the norm map. So we have our spectral curve from S to sigma, and we have a natural map from divisors. So if you have a divisor on S, Ni, Pi, you can take a natural map, the norm map, which will depend on our projection or our cover, and it will keep the same weight, and it'll do pi on the points Pi. So the norm map is what's going to allow us to see our line bundles in terms of divisors, and once we see them in terms of divisors, we can apply the norm map to our L, and the formula tells us that this is equivalent, this direct image is equivalent to the norm map of the line bundle, tensor with the pullback of k to the minus n minus 1 over 2. I think it's n minus 1 over 2. So you can see this by analyzing what the spectral curve is, where it lives. So this lives in the toroidal space of k, or really the pullback of k, and this is why your k appears here, and it's a very neat description of how to obtain this formula. But once you have it, the important fact is that now it's an equation in terms of L that we need to solve in order to put the condition on the line bundle. So the condition of triviality of the determinant of the vector bundle translates into a condition on the line bundle, and the condition on the line bundle is this one, is that the whole thing here is trivial, or equivalently, if you put this k inside, if you put, what do you have to put? If you put, can someone remember? Okay. Oh, sorry. Yes, what I want. Sorry, I don't want to put it inside the. Silly me. Okay, so I want to put the norm map outside everything, right? And the norm map and the pullback puts an n. So I want to put everything in terms of a condition in the line bundle. So it's going to be the norm map of L tensored with, and now I'm canceling the norm map with pi, canceling the n. So tensored with k to the minus n minus 1 over 2. I want all these to be trivial. So, oh, yes. Sorry. Oh, because the normal is downstairs. Yes, sorry. Now is the pi star. Yes, because the pi star is on the spectral curve. Thank you. So the line bundle, it's on the spectral curve. The pi star is on the spectral curve. This is the condition I want on the spectral curve. And so it's a condition on a line bundle to be twisted by something, but yet in the kernel of the norm map. The kernel of the norm map, so this is the kernel. So we want all these to be in the kernel of the norm map, and this is, by definition, the prime variety of this cover. Prime of S sigma. So the condition then is not for the line bundle that you started with, but for a twist of it to be in the prime variety, and your smooth fibers in this case will be a condition giving you prime varieties. So into a condition on a twist of L to be in the prime variety. So the twist is important, and it's important the fact that we have n-1/2. In some cases, you have to choose square roots. And when you choose square roots, you have choices that have to be accounted for. But the overall idea is that by putting the extra conditions on your vector bundle and on your Higgs field, you put conditions on your spectral curve and on your spectral curve from the Higgs field and on your line bundle from the vector bundle to describe the generic fiber. And now it's again generic in the sense of a generic point giving you a smooth fiber. So to obtain the fact that the generic fiber, in this case, the fiber over a point giving a spectral curve S is the prime variety S sigma. Now this is going to be, again, a twist, and you'll see how you'll have to choose k to the half in some cases, and you are, just by looking at the degree of this line bundle, you'll recover appropriately the degree 0 line bundles that you're expecting, because your SLNC, one of the implications of having trivial determinant is that you have 0 degree. So you have that already from your statement. By understanding now the map that goes just like we were doing before, the map that takes you from L to L tensored with the pullback of K. So now if you took the product from L to L tensored with the pullback of K, you can push it again down to the curve, the Riemann surface. So pushed to the Riemann surface gives phi from E to E tensored with K, which is traceless, because you're going to push a map and line bundles on a curve that doesn't have that factor, and that's where it's going to come. So this is going to be a few pages of calculations to see that it works. But there are very nice and straightforward calculations that will allow you to see that it works. Now, what would happen, and I'm about to finish, I have like 2 minutes. So what would happen if we put extra conditions? What would happen if we ask more things, not just for trivial determinant and trace 0, but if we ask, for instance, to have a symplectic Higgs bundle. So in the case of symplectic Higgs bundles, so note, and this I'll just finish giving you some hint of what happens in other cases. If you take GC equal to SP to NC, then what you're asking is for your vector bundle to have a symplectic form, so rank 2n, and it has with a symplectic form, let's call it W, and the Higgs field has to be compatible. So what you're going to say is that your W applied to two vectors, so V and then phi W, is going to be minus W phi V W. So there will be a condition on the vector bundle, a condition on the Higgs field. Those two conditions will tell you the structure of your Higgs field and will tell you the structure of your line bundle that will be pushed down. You have to have trivial determinant, so you will have to be in the prime variety, you know that already, but what other condition will you have to put on that object to be inside this curve? And if you want to understand what the spectral curve is, you look at the condition of compatibility with the symplectic form, and what it's telling you really is that the Higgs field is off diagonal. So from here, you see that if Higgs field has an eigenvalue, then it will have minus that eigenvalue also. So for any, and let me just conclude with this note, for any eigenvalue of phi minus the value is also there, is also eigenvalue. And then your spectral curve S has an equation that looks as lambda to the 2n, and all the odd degrees, because you only have even degrees because your eigenvalues come in pairs, all your odd degrees are not there, so you have something like A1 lambda to the 2n minus 2 plus A sub n, finish there, and your A sub i's are sections of H0 sigma k to a 2i. And you wonder what are the extra conditions that you would have to put on this line bundle to now give you a Higgs field that satisfies the conditions. Those are the conditions that will appear in the curve. And what are the conditions on the line bundle to give you this vector bundle? And what you note, and we'll see that it happens also for some real groups, what you note is because we have only even degrees, there's an involution that takes lambda to minus lambda. So there's an involution sigma that takes lambda to minus lambda. And the extra condition on your line bundle that was originally on a Jacobian of the curve, and then we saw that it was in the prime variety because we also need the trivial determinant. The extra condition now is that when we leave the action of the involution, it takes me to the dual. So really what this condition is telling you, if you have seen or worked with prime varieties before, what it's telling you is that, i.e., the line bundle has to be in another prime variety, which is the prime of the curve and the quotient of the curve by this involution. So there's a new prime variety appearing as the smooth fiber of your Hitchin fibration for the for the symplectic group, which we can deduce just because we started with the general linear group and we started putting conditions on that. So tomorrow I'm going to start by telling you how these dualities appear. You can see them a little bit because the Jacobian is self-dual, and that's the fiber being self-dual. The prime variety, which is the fiber for this, the dual abelian variety is the prime variety quotient by torsion endpoints, and that's the spectral data for this guy here. And we'll see the relation between these two. Once we have that, we can start looking at these branes inside, giving us either integrable systems or real slices, and we can see what the duality would be, all in terms of these spectral data. Thank you very much. Yes. Yeah. On the variables, you mean? You can define the, you mean with the Poisson bracket on the function? Yes. I think so. You know, Richard? Yes. Yeah, but this is another, do you want that action? I thought. Yes, there's a lot of things. Thank you. Thank you. Yes? Beyond, so you have your, just from scratch, you have your variables, then when you put your Poisson bracket, they commute, or? The way that Hitchin did it was by looking at those functions and finding the actual functions. But in this case, we have the mid-dimensional basis over these Lagrangian fibers. Thank you.